Okay, so this lesson we're going to talk about 10G, exercise 10G, multiple zeros. So what is a multiple zeros? It's like a double root, triple root. Whenever you have a polynomial equations, when you solve it, we know that for a polynomial equation, if it's a degree of n, then you have a maximum of n solutions. But sometimes you have like n minus one solution or n minus two solutions, just because of you've got a double root, okay? Or you can have like a triple root where you have the similar, the same factors, x minus alpha, x minus alpha, x minus alpha, and then x minus beta, x minus delta. So it can be like this. So you can have like a triple root, which all of those gives you the same answer, x is equal to alpha. Okay, so we can actually write down the root, the factors in terms of x minus alpha to the power of 3. Okay, so in this exercise, we're going to just talk about what's the behavior of a multiple roots, and then how is that related to the actual graph, and then what is that to do with the equation solving, how does that help us to solve equations, and what does differentiation doing here with the multiple roots. All right, so firstly, let's just start to write down if we have a polynomial function that has a multiple roots. In that case, we can actually write down the p of x equals to x minus alpha to the power of m times by q of x, okay? Where q of x is not divisible by x minus alpha. All right, so if you just look at this expression here, clearly you can see that x minus alpha is a factor, so x is equal to alpha is a root. That power of m tells you, what is the multiplicity. Could be like a double root, it can be like, a triple root, depends on what's the power here equals to. If it's a power of 2, then it's going to be a double root, since because if it's a power of 2, you can actually separate these factors into x minus alpha and x minus alpha when they multiply together. All right, so therefore the value of m just tells you what is the multiplicity of the polynomials, okay? So the value of x equals to alpha is a 0 of multiplicity m of the polynomial p of x. All right, and then remember that if q of alpha is not equal to 0, otherwise it doesn't make any sense, right? Because when you do the normal division, you need to have the quotient on the top. Okay, all right. So, how does the multiple zeros related to the differentiation, and how are we going to use the derivatives to actually solve equations? So what is sort of the relationship between multiple roots with the derivatives with the curve sketching? So if you think about a mind map, all right, so we have multiple roots or multiple zeros. Now, this multiple zeros is actually related to the derivatives, okay? So it's related to the first derivatives, it's also related to the second derivatives, it's related to the third derivatives. This depends on what is the multiplicity of the multiple roots, right? Then, when we're dealing with the derivatives, then it's also talking about the stationary points. So it's actually related to the stationary points as well. All right, especially when it comes to the curve sketching. So this is actually very important as well. It does relate to the equation solving. All right, how do we use the information of the multiple roots to solve the equation, to help us to solve the equation? So hopefully that's a bit easier for us to actually solve a very hard polynomial equation if we do know certain things about multiple roots. And then it's about factorization as well, of course. Part of the equation solving method is you're able to actually factor in, okay, the polynomials. Sometimes the question can be related to the root and coefficient relations. So it's like in the sum of the roots, the product of the roots. Okay, so root and coefficients relations. All right, so in this lesson, we're just going to talk about all of those factors here. Okay, all of those. All right, so the first thing we do is let's move on to the derivatives, okay? How is the multiple roots actually related to the differentiation, and how are we going to use the derivatives to actually factorize and solve the question, or check if the function has a, if the equation has a multiple root or not? All right, so firstly, let's just start with this. If we have a p of x is equal to x minus alpha, all right, and then q of x, or to the power of m times by q of x. Now let's just have a look at what happens, okay, if we start to differentiate. This is extremely important, all right, if we start to differentiate what's going on. And then I'm going to differentiate again, and we'll see what's going on. Right? And then I'm going to tell you what's the properties and what's the relationship between the multiple roots and the derivatives. So right now, so we know that x equals to alpha is a root of p of x. Okay, it's a root of p of x. Right now we know it's like a multiple root, but let's just say that's a root of p of x. I don't know if it's multiple root or not. Okay, now if we differentiate this function, okay, this is just going to be a product rule, as you can see. As you can see here, that's a function here, and that's another function there. So it's going to be a product rule. So you're going to use the product rule method to actually differentiate. All right, so the first step is you actually differentiate the first function, which you end up with this. Then you times by the second function q of x. Then you plus, you differentiate the second function, then you times by the first function. All right, so this is what a product rule is. All right, once you finish that, you actually need to factorize, okay? What you need to do is you factorize the common factor between this and that one there. All right, remember, you always take a lower power out. So in this case here, you are taking x minus alpha to the power of m minus 1 outside when you're factorizing it. Okay, so plus x minus alpha to the power of 1 q dash x. Now the reason it's to the power of 1 here is if you're using your index law, when you times these two terms together, the base are the same, so you actually plus the power together, which m minus 1 plus 1 is equal to m, and that is equal to the m there. Alright, so all of those, right, is a function. So in this case here, what I can do is replace this function by another term, so I can call that the k of x. Okay, just replacing all of those into k of x. It doesn't really matter. All right, because what I really want to show you here is, if you just look at this expression here now, this is p dash x. That one, when x is equal to alpha, if we substitute x equal to alpha, that that entire expression here still equals to 0. That's the most important part. So that looks like alpha is still equals to 0 for the first derivative function, which tells you that if I substitute alpha inside, that's equal to 0, and then somehow we can use this method to actually show if there's a double root or not. Okay, so therefore we can say x equals to alpha is a root of p dash x. Now we can continue this process by finding p double dash x, and by keep differentiating this. Okay, you end up with the same sort of expression again and again and again. So you end up with this time x minus alpha m minus 2, not k of x this time. It could be like p, not p of x, but it could be just t of x, another another crazy expression inside, but then x equals to alpha is a root of p double dash x. Okay, all right. So what does that mean, and so what is the effect of this? What does that mean is I'm just going to write down what the textbook tells you, and then I'm going to put this one into sort of like a much easier way for you to understand what's going on. So the text was summarized as this. Okay, so what the text was saying is, let x equals to alpha be a 0 of multiplicity m greater than or equals to 1 of a polynomial p of x. So basically what the textbook says, let x equal to alpha be a 0, so be a root, okay, of a multiplicity of m greater than or equals to 1. So it could be a double root, it could be a triple root, it could be any root that, it could be any, a multiple root of a polynomial p of x. Then the most important fact here is x equals to alpha is also, okay, a 0 of multiplicity m minus 1 of the derivatives of p dash x. All right, now for some student, they probably like find it. What does that mean? What is this? What's the meaning of this? What is mean by the derivatives, and how does that work with the derivatives? What is meaning here is if we have a double root, all right, for the polynomials, then the derivative of that polynomials, if you substitute the alpha inside, okay, will also equals to 0. Okay, so it means that if for us to know if the function or if the equation has a double root or not, all we have to do is we differentiate, and then we solve the derivative function and find out the 0 of the derivative function, and we confirm if that 0 is going to be a double root or not. Okay, for a root to be a triple root, then p double dash x must be equal to 0. Alright, so it's actually following this idea here. So I'm putting this one into an example. Alright, I'm going to show you what's going on with the triple root and with the double root. It's much easier to show it as an example instead of just reading through this entire lines of an explanation. Sometimes the students don't really understand what's going on. Alright, before I show you the example, I just want to show you a sort of a flow chart. So it's to prove. Okay, prove a polynomial function that has a double root. Okay, the process here, or the steps here, is what you need to do is you need to first step, step 1, you're going to find, since we're proving the double root, okay, so double root, we only need to find the first derivative, so we're going to find p dash x. Alright, and then step 2, we need to solve p dash x equals to 0. And step 3, okay, so let's just say if we solve a p dash x is equal to 0, we've got x is equal to alpha, beta, dot, 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 dot. It can be multiple solutions to have a multiple root. Then we're going to check x equals to alpha, beta, dot, 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 with the original, with the original function into the p of x function here. So we're going to check this, and if p alpha, p beta, dot 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 is also equal to 0, then alpha, beta are the double root, dot 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 dot. So that's the idea, okay? That's the flow. So if you want to prove certain things has a polynomial equation has a double root or not, you just differentiate that. You solve the derivative equation, find the zeros, and then you substitute those zeros back into the original function. If they are equal to 0, then each one of them are the double roots. If one of them is equal to 0, that means this is the double root. If that's not equal to 0, that means that's not the double root. Okay, that's the idea. All right, so put this one into an example, a very simple example from the textbook. I'm just choosing an easy one. So question 3 from the textbook. It says we've got a polynomial function p of x is equal to x to the power 3 minus 27x plus 54 has a double root. So we know this function, this polynomial expression will have a double zeros. Okay, so now the first question here asks us to actually find the zero of, find the zeros, of p dash x, and then eventually the question asks you to find all the zeros and to determine which one is the 0. So in this case here, I'm just going to remove the actual question here. What we are going to do is, it seems we know this one has a double 0, so how about we find those double zeros out? All right, so the steps here, if you follow the steps here, we're going to differentiate that. All right, so if we do the p dash x, that is equal to 3x squared minus 27, and we need to make sure we solve this p dash x is equal to 0. So solve this equation. Okay, so x squared is equal to 9, and then x is equal to plus minus 3 here. Now you've got two solutions. You need to check which solution gives you the double root. Okay, not all the solution gives you double root. If you think about it this way, if both positive 3 and negative 3 is a double root, then you will end up with 4 roots. All right, but this one is power of 3 here, so you shouldn't have 4 roots. You only have 3 roots as a maximum. So you can't guarantee that every single time when you let it, the derivative p of x is equal to 0. When you solve this, answer here, that's always a double root. You can't guarantee that. You always have to check. So now we just have to check. So we check p3, and we check p negative 3 to see which one gives us a 0 here. All right. So we check P3, that becomes 27 minus 27 times by 3 plus 54. That is equal to... Okay, I don't have my calculator with me. I think my boys took my calculator as their... Oh, I have to use my iPhone calculator this time. Sorry. They're just taking my calculator away to use as their phone. Okay, so that is equal to 0. Okay, good. That's promising. So that actually tells us x equal to 3 is a double root. Okay, so again, let's just check the next one. It's a negative 27 plus 27 times by 3 plus 54. All right, so clearly this is not equal to 0. All right, so now you can make a conclusion by saying that, so therefore x equal to 3 is a double root. All right, so therefore that means you have like alpha and beta, they're both equals to 3. Now, if I want to solve this equation here, making this is equal to 0, you can either use the long division to solve for the last root, but you can also use something that's really simple, and that's something we have learned before about root and coefficient relations. All right, so we know that alpha plus beta plus gamma is equal to minus b on a, and we know one of the two of the roots are double roots. One of the roots is double root, which means we know 3 plus gamma is equal to minus b on a. Now with minus b on a here, have to be very careful. Although this looks like the second term, but the power is equal to power of 1. It's not power of 2, so that's not b. All right, so b term is actually missing. All right, so therefore minus b on a is actually equal to 0. So therefore gamma is equal to minus 6. So now you have 3 roots. These are the 3 roots. X equal to 3, x equal to minus 6, and x equal to 3 again. All right, well, technically it's 2 roots, but one of the roots is a double root. Okay, so 3 and minus 6 are the roots of this polynomial p of x. So this is the idea. All right, now this is how we solve for a double root. How do we know if a function has a triple root or not? Okay, now for a triple root, same thing applies. All right, so I'm just going to copy this one down because it's very similar. For a triple root, or for like even higher like a multiple of roots, the way we do it is very similar to as a double root question. Very, very similar. The only difference here is we just need to do one more differentiation. Okay, just one more differentiation. So if it's a triple root question, all right, first step here is you need to find p dash x, and you also need to find p double dash x. All right, so both. Then what you need to do is you actually solve, instead of solving p dash x equal to 0, you're going to solve p double dash x equal to 0. Okay, you're going to solve the second derivative equal to 0. And obviously you're going to, you probably have multiple roots there. And then you are going to check this time. You're going to substitute the numbers that you solve after you're solving p double dash x equal to 0 into not just p of x. You need to substitute into p dash x and p of x. You need to prove both p dash x and px, and those those numbers that you substitute inside is equal to 0. So that means you actually need to also prove that this and that is also equal to 0. Then you can confirm the roots are a triple root. Okay, so this is the idea. Now, if it's a quartic root, like you've got like 4 roots, they're repeating themselves, that you're going to differentiate 3 times, and you're going to solve the third derivative equal to 0, and then you have to substitute and check into the second derivative, into the first derivative, into the original. And that will be the steps to do it. Okay? All right. So you can actually try the questions in the exercise. Question 4 is about the triple zeros, triple root question. So have a look at this message here. It's actually very important. Now, the most important thing is you have to check. Okay, don't just assume that if you let second derivative equal to 0, the numbers you're getting is a triple root automatically. You have to check into the first derivative, make sure the first derivative gives you 0. You have to check into the the original function, make sure that also gives you 0 as well. Otherwise, it's not going to count. All right. So this is how the multiple zeros is related to the derivatives. All right, and then that's how we actually can factor in polynomials and also solving the equations later on. All right. Now I'm going to show you, okay, it seems that we have done this, right? So now we'll move on to the factoring and solving equations. So how do multiple zeros help us to actually solve equations? To be honest, unless the question tells me this polynomial equation has a double root or triple root, usually I'm not going to use the double root and triple root method to actually solve the equation, because you just don't know, okay? You just don't know if a function of an equation has a double root or if the equation has a triple root or not. And then you can check, but I feel like in the checking process will be a bit longer. I'll probably just solve the equation anyway, so instead of checking. Okay, so this is the the suggestion I give to you. Unless the question tells you this polynomial function p of x has a double root, solve it, then you're using this method. Otherwise, don't use this method. Okay, it will take a longer time. I do want to show you example 19, so like a solving equations. In example 19 from the textbook, okay, they were saying that, okay, factor the polynomial p of x equals to x to the power 5 minus 8x to the power 4 plus 25x to the power 3 minus 38x squared plus 28x minus 8 completely. All right, they are using this example as for a purpose of they want to demonstrate this question here. It's a degree of 5, so you have a maximum of 5 solutions there, or 5 zeros. But then they sort of design a question, want to prove a point where you can use the method by differentiating it and check and solve and see if there's a triple or double root. But then the problem here I have here is if you do get a question like this in the exam, in the real exam, you don't know. You don't know if the question has a double root or triple root. You can check, but as you can see, the checking process actually takes a bit of longer time, especially if it's a triple root. You have to check for both first and second derivatives. So my suggestion is, if you do get a question like this, you find the answers, and then you sort of do long divisions. Okay, I still go towards long division, sort of like a way of doing the question. All right, anyway, I was just, okay, we'll do this question, and we pretend that this question has a triple root, or at least a double root. Okay, and then we'll see if that's true or not, and then eventually we'll solve it. But remember, this is not going to be my method to actually solve this question in a real exam. In a real exam, I'm just going to check the root, and then I'm just going to use the long division to actually factorize. Okay, so we've got p of x is equal to x to the power 5 minus 8x to the power 4 plus 25x to the power 3 minus 38x squared plus 28x minus 8. Alright, so the next step is I am going to assume this one has a triple root. Now, another issue is, how do you know this one has a triple root or maybe a quartic root? You don't know. So, what's the derivative that you need to get up to? You don't know. Alright? So, if we differentiate first time, okay, we get this. Alright, so we'll get this this function here if we differentiate the first one. We can differentiate again. So if we differentiate second time, we'll get 20x to the power 3 minus 96x squared plus 150x minus 76. Now, we can actually differentiate another time, okay? But then the problem here is, if you differentiate another time, okay, how do you know if it's, it's a quartic root or not? You don't. Alright, so second derivative, I'll stop at this point. I'll assume this one has a double root or triple root this time. Okay, so I've got all of those. Now I'm going to still use the method by letting x equals to 1 and check. Okay, so we're going to check P1. Right, I want to see if 1 is a solution or not. Again, I don't have my calculator with me. I should get my calculator. They're just taking my calculator away and play. Okay, I'm just using my iPhone calculator. Yep, that is equal to 0. Alright, so x equal to 1 is equal to 0. Now, alright, we need to check if this is a double root or not. If it's a double root, then p-1 is also equal to 0. So we need to check that. If it's not a double 0, then this is not equal to 0. Okay? Alright. Negative 27. minus 1 plus 28. Ah, yeah, that is equal to 0. Good. I need to check one more time for the p double dash 1 is equal to what number, because I want to see if x equal to 1 is a triple root or not. All right, who knows? We don't. All right, we don't know. So therefore, we can do that. So 20 minus 96 plus 150 minus 76. Just using my calculator. Check again. Alright, so that's equal to minus 2. So, therefore, from here, we can make a conclusion that from this 2, x equals to 1 is a double root. Alright? It's not triple roots because, if p double dash x is never, it's not equal to 0 this time. Alright, so, yep, that's good. We've got a double root, but remember this is power of 5 here, so we need to have another 3 roots here. So we haven't finished it, okay? We need to continue the process. Alright, need to check. Maybe this time p2. Alright, check 2 this time. 32 minus 8 times by 2 to the power 4. Plus 25 times by 8. Minus 38 times by 4. Plus 28 times by 2. Minus 8. Now, I've got the answers in front of me, so I'm just a bit lazy this time. It's actually equal to 0, right? So P2 is equal to 0. All right, so we know that is a root, okay? But we don't know if that's a double root or not. So to check if it's double root, we substitute that into P dash X, okay? Alright, and then according to the answer, that is still equals to 0. Good. Alright, so we now know this is the double root. Again, we just need to put and substitute into this third one, and to check if it's a triple root. Alright, so that is 160 minus 384 plus 300 minus 76. According to the answer, yes, it is equal to 0. So from here, you can make a conclusion that, x equals to 2 is a triple root. Alright, so once we got this information, that's a triple root, and that's a double root, then we can fully factorize this polynomial. So now p of x is equal to x minus 1 to the power of 2, since this is a double root, and x minus 2 to the power of 3, because that's a triple root. Now this example, it's not a typical example like in exams where this is the suggested method that you go, okay? Because again, the question is designed where they want to show that this method works. But remember, in a real situation, you don't know how many, whether the number is a double root or a triple root at all. So what I suggest you is always use a combination method, all right? Don't just use one method. Use a combination method. Yes, you can try to differentiate, a couple of times. You can try to substitute into here and into there, and to see if a number is a double root or not, or triple root or not. But once you actually confirm something, okay, you might be thinking about using other way to solve other other roots, instead of like you check it again. All right, just remember it's designed in this way. The 2 works. Sometimes it's probably not going to work. All right, so you're going to waste your time by keep checking it. So rather just do maybe a long division that can help you to actually solve the question. Okay. That's the idea about using the multiple roots to solve the equation. Okay, the next one we're going to move on is the stationary point. Okay, how the double roots actually help us to do the stationary point. Now remember the previous lesson about when the 2 polynomials intersect each other, and then I said to you how do I know if the 2 curves that actually touch at each other, or how do I know if the 2 curves that actually intersect? Now we can actually answer this question, okay? Think about the p of x. If we have a factor like this, like m and x minus beta n, think about it. If m is greater than or equals to greater than 1, and m is an even number or even integer, then in that case, the conclusion for that is if you want to draw the diagram, okay, sketch the curve here, then the curve will have a stationary point, Okay, so if x equals to like alpha, if x equal to alpha has an even multiplicity, okay, which in this case m has to be an even integers, then the curve is actually a tangent to the x-axis. Okay, curve to is tangent to the x-axis at x equals to alpha. Now we've done this before, okay, when we're dealing with curve sketching, so this is not new to you. All right, next one is if m is greater than or equals to 1 and not equals to 1, just greater than 1, and or n this time, and n is an odd integer, so therefore we have x equals to beta is has an odd multiplicity of at least 3, then this time the curve, it is still tangent, okay, to the x-axis, still tangent to the x-axis, but this time, okay, crosses the x-axis. So we call this the horizontal point of inflection. Again, eventually, like later when we're dealing with the curve sketching, I will tell you what's the horizontal point inflection. So it actually crosses the x-axis. All right, so this one does not cross the x-axis. All right, so this is actually pretty important, okay? If it's power of 2, it does not cross. If it's power of 3 or 5 or 7, it crosses the x-axis, but still it's a tangent, okay? So if x equals to alpha, it's a simple 0, like a degree of power of is equal to 1, that just means there's no stationary point. Now, we've done this before when we actually sketched the curve sketching before, right? So it's like, if we need to sketch p of x is equal to x minus 2 to the power of 2, x minus 3 to the power of 3, like for example this. We've done this before when it comes to the curve sketching with the polynomials. All right, I remember the first step to do is identify the zeros, which is 2 and 3. So I've got like 2 and 3. And then, look out for the leading coefficients. The leading coefficient is positive, so the curve is stuff on the top right. And then we're going to go through. This is the power of 3, which is, an odd number, and then it's high, it's odd number at least with a multiplicity of 3. So it's going to be a tangent but cross, okay? So therefore the curve looks like this, okay? It's going to be a tangent. And then to the power of 2, so the curve is going to be, a turning point like this, okay? So it's going to be still a tangent. So as you can see here, these 2 points, there's still a tangent to the horizontal axis. However, this one is actually across the x-axis with the power of 2 or power of 4 or power of 6 and an even multiplicity. The curve is just going to touch without crossing the x-axis. All right, so we've done this before. All right, so this is not really new to you guys, but now it's sort of like formalized the process. We know the reason behind it, okay? All right, okay, that's all for the multiplicity, and that's all for the multiple roots. All right, please try the questions in the exercise. Now, with multiple zeros, previously this concept here, this entire concept of multiple zeros, were in the extension 2 topic. But now they changed the syllabus, they moved this down to the extension 1. It's not that hard, to be honest. The question itself is actually pretty straightforward as long as you understand what's going on. All right, let me know if you have any questions. Thanks for watching.